The free body diagram. This is probably the most important topic in all of mechanics. So I want to go through this very carefully. Before we get started, just a quick reminder of where we are right now in statics, but really in all of mechanics. So we started in chapter 1. This was just an introductory chapter. We talked about units, significant digits, rounding. We talked about the term mechanics. And so remember, the subject of mechanics is we're studying forces that are applied to bodies, solid, liquid, or gas bodies, and the effects that these forces cause on the bodies. We study mechanics of liquid and gas bodies in fluid mechanics. But the introductory course to mechanics is typically statics. And so we start by studying vectors, vector operations in general. In particular, we look at force vectors and position vectors. But it's not enough to just study forces, because there's also the idea of the rotations, the torques that forces cause, right? You can have two of the exact same forces, but depending on the location of that force, one force has a more significant effect on the system. Like you think about a wrench. The same force on a longer wrench has a different effect. So we also study the concept of the moment of a force, how to calculate a moment. Moments about points, axes, couple moments. Now, these concepts of vectors and vectors as forces and moments aren't unique to statics. This is general in mechanics. We're going to apply these concepts in all of mechanics. Statics, dynamics, fluid mechanics, mechanics of materials. So you can think about it like when studying forces and moments, we haven't really started statics yet. We've been building a foundation to study mechanics in general, studying forces and moments. Now, before you can think about, kind of start statics, we have one more foundational step to go. One more piece of the foundation that we need to lay in order to study mechanics. We need to learn how to make a free body diagram. And that's what this video is about. Now, you might be asking, what about chapter 3? As far as the story of statics goes, you could put chapter 3 inside of chapter 5. Right? This is equilibrium of a rigid body. All this is a special case of equilibrium, but it's of a particle. In chapter 4, when we were going through section 4.7 and 4.8, which talked about how to simplify force systems, you could take a force system and simplify it to a couple in a moment, or even a wrench. We talked about certain special cases in section 4.8. So, for example, the parallel force case or the coplanar force case. In that case, you could simplify an entire force couple moment system to just a force with no couple moment. But there was also the special case of a concurrent force system. This was in 2D or 3D. That's where the lines of action of all of the forces on the body meet at a point. Well, in that case, what you could do is you could slide all of the force vector tails to that point, do a vector sum, and replace all of the forces by a single resultant force. But for this case, for the free body diagram, what you could do is you could use the particle assumption. You could model the entire body as just a particle at a point with all of the forces at that point. For the case of static equilibrium, that point didn't have to be the center of mass. For the dynamic case, if the object is accelerating, then it had to be the center of mass. And that's what chapter 3 was about, the equilibrium of a particle. It came before chapter 4 because moments aren't involved for concurrent force systems in 2D or 3D. All right, so what is a free body diagram? Well, for the rest of this video, I'm going to use solid bodies as examples, which are modeled as rigid bodies in statics and dynamics. In statics and dynamics, the solids are assumed to be rigid bodies. But just note that once you get really comfortable with creating a free body diagram for a solid or for a rigid body, the majority of those concepts extend to free body diagrams on liquids and gases. There are some subtle differences that I'll talk about in those courses. But again, the vast majority of the concepts that you need to understand about free body diagrams, we're going to talk about here. Okay, let's take a look at this bobcat here. With a free body diagram, what you're doing is you're taking any component off of this bobcat, any component or any group of connected components. And then what you can imagine is you bring that component or components into empty space. Empty space meaning so there's no planets, there's no forces on it, and it's just suspended in nothingness. So let's imagine let's just say we took this component here. So we're not taking a group of connected components, we're just taking one component. We bring it into empty space. We remove it from being connected to the machine here and bring it into empty space. But now that we have it in empty space, what we want to do is we want to add all of the forces to it. Add forces to it so that even though it's in empty space, it's still an equivalent representation of how it was connected here, right? So we want to bring it into empty space so we can analyze it. We're trying to analyze the forces on it. So again, we bring it into empty space, but then once we have it there, we want to pictorially apply forces to it so that it's kind of like we didn't remove it. It's kind of like it's still connected here, but now we can analyze the forces on it. Okay, now some things to note. When we bring this connection into empty space, it depends on the snapshot in time that we do this. So we could bring it into empty space right now where there's no load on the machine, the shovel is down. But really more commonly, the idea is if you're designing this machine, you'll look at what's a standard operating scenario. So a standard load in the bucket, and it's raised to like mid-height. That scenario. So take a snapshot of that, and at that moment, bring this component into empty space. And then maybe you'll analyze some worst-case scenarios. So fill the bucket, overfill it with gravel or cement, raise it really high in the air, take a snapshot there, and then bring this component into empty space and apply the forces then. That'll be two different free body diagrams for those two different scenarios. Or the designers might say, well, another potential worst case scenario is the bucket is overfilled, it's raised up high, and then it's accidentally dropped full speed. And so kind of midway down, it's the largest acceleration. And so you'll analyze this from a dynamic standpoint. But still, when it's on its way down, it's accelerating, you take a snapshot and you bring this component into empty space. Now, the free body diagram, in that case, you'll have to specify its acceleration as well, the component's acceleration. But I don't want to get too much into dynamics here, but I think you get the idea. In statics, we're more talking about snapshots in time where it's still. Everything is still. Or moving at constant velocity, but much more commonly not moving. Okay, but so we bring this component into empty space. Let's come back to the standard operating position. We bring it into empty space, and the next step is we want to add absolutely every single force that was acting on this body when it was present on the machine in that snapshot state. Every single force. We started off, we removed it, we put it in empty space, completely isolated from any environmental factors. Now we want to add all forces that were acting on the body when it was present in that snapshot position. So you can think about it like in empty space, we're trying to recreate the exact loading scenario on the body that it was under in that snapshot position. And so if in that snapshot it was not moving, the velocity was zero, then when we apply the forces, all of the forces on the free body diagram in empty space, then it shouldn't be moving. If we applied the exact load scenario that was present in that snapshot, right? If the component was accelerating at that snapshot, then when we apply the loads in empty space, the components should be accelerating just like it was at that snapshot. We have to apply all the loads. We can't miss a load. Now you might be saying, well, how can I account for all loads? I mean, what about, this Earth's magnetic field could be causing a force on this? What if a bird flies and lands on it and, the bird's going to exert a force on it? Okay, let me give an example. I don't design bobcats, but there's a chance that when this is in like an operating position, so it has its operating load on the plate, in a lot of situations, designers will neglect the weight of a component in the free body diagram because the weight of the component is small compared to the weights in the links. So its effect on the free body diagram is negligible. So really it's more, you have to apply every single force that has a significant magnitude to where it's pertinent to the problem, to where it affects the load equilibrium or the load dynamics of that body. A bird flying and landing, that force would be completely negligible. You don't have to consider that. but you cannot miss a force that has a pertinent magnitude, or else your free body diagram will fail. And then once you have a correctly constructed free body diagram, then you can move on to the more official statics or dynamics analysis where you apply Newton's second law. All right, so let's do an example of a free body diagram just so you can start to get a sense of this. All right, so we want to make a free body diagram of this foot lever here. Here's an image of the setup. So again, what you do is you take the component that you want to make a free body diagram of, and imagine you remove it from its environment and put it in empty space, completely isolated in empty space. Right? So this is exactly what it would look like. Isolated, no forces applied to it. You got these holes here. Here's the component. And I say empty space because it's important that you start off by isolating this from absolutely any environmental factors. Okay, now next, we want to apply every single force. We can't miss a force that has significant magnitude. So how do we do this? Well, okay, we know there's only two types of forces in the universe: body forces and surface or contact forces. Let's start with body forces. There's only three body forces: gravity, electricity, magnetism. Now, technically, if you're working in an accelerating reference frame, then there's other body forces, fictitious body forces like centrifugal type forces, but that's a far away subject, and most of you probably won't even ever need to learn that. So we're dealing with a non-accelerating reference frame, the vast majority of the time a non-moving reference frame. In that case, there's only three body forces to consider: gravity, electricity, magnetism. Gravity, so the weight of this connection. We're going to neglect the weight of this link. We're going to say that the weight of this link is negligible compared to the forces that are going to develop as a result of this foot pushing down. Now, we're not going to do a full analysis on this, but for problems in the future, if you want to work a problem where we neglected the weight of the component, get the answer and then go back and rework the problem with putting the weight in, and you can see for yourself that how in a lot of circumstances the weight has negligible effect on the final result, the weight of the component. Okay, so gravity forces are that's it. No more gravity forces. Electricity and magnetism, you'll know if electric or magnetic body forces are part of the problem. You can think about if you're working with an electric motor, right? Those are built with these solenoids that they've got these huge magnetic fields that are a part of the problem, electric and magnetic fields. Here, there's obviously no electric or magnetic body forces that are a part of the problem. We've accounted for all the body forces. There's no body forces. But it's really helpful that we've now accounted for all of the body forces, because there's only one other type of force in the universe, a surface force, contact force. What does that mean? That means that any force that's acting on this link is going to come from contact with something. If there's no contact, there's no force. There has to be contact. I'm going to say this again because it's really important and really helpful. Once you've accounted for the body forces, then all other forces on your free body diagram, on your component, is going to come from contact with something, right? If you come back to the environment it was in, there has to be contact with something for there to be a force. There has to be contact. Okay, so we see there's contact with the foot here. There's contact with something at this pinpoint. There's contact here and there's contact here. So there you go. That's the only forces on this link, forces of significant magnitude. Okay, but the next thing to think about is these contact points. The force at these contact points is going to be distributed over the contact area. Is the size of that contact area significant compared to the size of the link? Here we can say the answer to that is no. So in other words, we're going to just put point forces at these points. We're not going to worry about the load distribution. Well, you might say, well, how do you know that? I mean, that's pretty, these pinholes are kind of big. How do you know that? Well, this just comes with experience, but the way you can think about it is, so what we're doing in statics and even dynamics is we draw these free body diagrams. We make sure that we draw them accurately. They have to be drawn correctly. That's so important. We have these correctly drawn free body diagrams, and there's known and unknown forces applied. And then from there, because we have some known forces, we can solve for all the unknown forces. So here, for example, the pin force is unknown. So we solve for the unknown pin force, and we can use that information to get the size of pin we need and the strength of pin we need. In statics and dynamics, we're just trying to solve for all of the forces, every single force that's acting on something. We want to know all of the forces. Okay, well, you can think about if you decided to put this as some sort of distributed load. And same here. This is a uniformly distributed load, but you could go, you could take it to the extremes. A pin distributed load, if you do like a FEA analysis, it's probably like, it's higher towards the center. If you did all this, same here. If you went to all this detail, you solve for the unknown forces in the pin. I don't think we don't know the force in the foot from the foot actually either. So you solve for the force in the foot and the pin. And then you came back and did it with just point loads. The result you get for the forces in the pin is going to be you won't notice any difference either way. Okay, the more statics problems you work, once you work more statics problems, you'll get a feel for when it would be necessary to put a distributed load or not. If you had a load, if you had some large body acting over this entire span of the link here, then yeah, you're going to need to put, a distributed load and analyze it that way. Okay, so we know all of the contact points, so we know where there's forces. What we need to do is apply all of the force information. There's going to be force information that we know and force information that we don't know. Knowns and unknowns. You'll see people talk about like unknown forces and known forces, but you might know a force magnitude, but you don't know its direction, for example. So I'm just going to say force information that you know and that you don't know. What type of information about a force is there that for you to know or not know? You have the force magnitude, the force direction, and the force location, the force position, right? Maybe this force is here instead of here. And you can also think about that on like a component basis. Maybe you know the X component of a force, but not the Y component. You could break it down that way too. Or maybe like if you're working in 3D, you know the one direction angle or two direction angles of the force, but you don't know the third, right? You know alpha and beta, but not gamma, for example. When it comes to the force information that you know, it's important that you put the correct information. You have to get that right. We'll talk about with unknown forces, you could put the wrong direction and it doesn't matter that you'll get the correct direction when you solve the problem. But when it comes to known information, you have to get it right. You have to input it correctly, or else your problem's going to be screwed up. And then not only do you have to put the correct known information, you need to make sure that you analyze the problem carefully to make sure that you're putting as much known information as you can. Okay, for example, here, in this problem, they give the stretch of the spring. They tell you that the spring is stretched, and they tell you about how much. So because they tell us that the spring is stretched, we know that the spring is pulling in this direction. I mean, they could say that the spring has been extended by this amount, but maybe the spring started in compression and it's still in compression, so it's still pushing back. Like you have to get the knowns correct. Like the knowns is you understand the problem. You're the one that's designing the problem, so you have to apply the knowns correctly. Maybe you do have a spring that's starting off very compressed and then it's stretching a little bit, but it's still in the compression state, so you know the spring is pushing this direction. Right? You define the problem. So you have to put in the knowns correctly. So again, but here they tell us that the spring is stretched and they tell us by how much. So we know the spring constant, right? So you buy a spring and it'll tell you the spring constant. So we can determine the force from this spring, right? So you can't by mistake put this spring force acting to the left. Like that would mean the spring is in compression. You're going to screw up your problem. It's not going to tell you that you did that wrong because you're defining the problem. The knowns you have to get correct. So you put the known spring force based on the stretch of the spring from equilibrium times the spring constant, and you put the direction. Now we can see, we'll learn that about two force members later in the chapter, but for springs like this and for links like this, we know that the force is acting along the line of action of these components. We can see that it's effectively horizontal here. Same here. So we're gonna put these forces as horizontal. We're not gonna put an unknown theta. But maybe you do need to put an unknown theta. It just depends. It just depends. Or maybe the spring is at an angle, but you can do Photoshop on the picture and you can measure what that angle is. So then you'd put the angle of the force, the spring force, the magnitude of the spring force, and you put that angle that you measured. Or maybe it is an unknown angle. You're trying to figure out, where do I mount this spring here? Do I mount it up here? And so it is an unknown angle that you want to solve for. Okay, but here it tells us the stretch of the spring. It stretched 1.5 inches. So 1.5 times 20 is 30. So this is 30 pounds. And the spring is in tension, so we know it's pulling in this direction, and we can see it's horizontal. It also tells us, we know the force in this link here is 20 pounds. And we can see the link is horizontal. Again, we'll learn about two force members later, but we know that this force is horizontal as well, along the axis of that link. Okay, but I just want to point out again, these happen to be the knowns for this problem, but maybe, and the unknowns is going to be the forces in the pin and the force in the foot. But maybe we know the force in the foot. Maybe we're specifying the force in the foot, and we want to use that information to find out an unknown spring force, because we're going to buy a new spring. We're going to buy a spring. And we want to know what spring constant of spring do we buy. So we're going to solve for the unknown spring force. It just depends on the problem. But again, you have to put the correct knowns, and you have to be careful that you apply as many knowns as possible. If it's unnecessary to put an unknown theta here, right, to call this an unknown theta, it's effectively horizontal, then don't do that. Don't put an unknown theta. Make smart assumptions. But if you have to have an unknown theta, then do it. Okay, so we've got the force magnitudes and directions and also their positions. We're not going to just put this force here. No, we know its position. Its position's there. So get all of the known information right. Force magnitudes, directions, and positions. All right, so we've got all of the known information, the known force information. Next, we need to apply the unknown forces or unknown force information. I'm saying force information because, well, we know this force from the foot. It's an unknown force, but we know that force is not here, right? We know the force is here, and we actually know it's acting down. But okay, so you want to include only as much unknown information as you have to. So here we're assuming the foot force is acting straight up and down, this unknown foot force. But if you had to, you could put it at an unknown angle, or what you could do is you could solve one free body diagram with the foot acting straight up and down, and then one acting at a 45-degree angle. You could do it that way. But what is nice is that when it comes to the sense of unknown forces, so the sense being, is this positive or negative, acting up or down? As long as you put your known information in correctly, all of your known force information, then the final answer will tell you what the correct sense is. If you put the wrong sense, then the final answer will be negative, so you'll know the force is actually acting in the opposite direction of which you put it. So for unknown forces, you don't have to worry about the sense. Just put whatever sense you want. But again, you could still put this at an angle if you wanted to, but that adds another unknown. So if this angle was 0 degrees, and if you had sufficient knowns, you'd solve for this, and it would tell you that it is 0 degrees. But this is different than the sense. This is like an extra unknown. The sense of an unknown force is not an extra unknown. The final answer will just tell you. It'll say positive or negative, and it'll tell you. So, okay, but we're assuming vertical. We know the location of this force, 5 inches from this pin. I'm not going to put the dimensions here, but in a free body diagram, you technically want to put all the dimensions of all the forces, their locations relative to the whole body. But we've got one other point of contact to account for. It's here, this pin here. Okay, we're going to go into more detail on the types of connections later in the video, but for a pinned connection, if you think about it, it's preventing any translation of this link. This link cannot move in any direction. The link can't move. It can rotate, but it can't translate. That's the idea of a pin connection. A pin prevents any translation, but it allows rotation. So what that means is that we have an unknown force and an unknown direction of that force. So you could put, if this is the X and Y axis, you could put an unknown force, we'll call it A because it's at point A, in an unknown direction. And with unknown forces, just put any arbitrary direction because the sense, the final answer is going to tell you the sense. Or what's more commonly done is you do it this way. Instead of specifying a force magnitude and an angle, you just put a y, a x, and you just put them in the positive directions, right? We're assuming that's another thing you want to do with the free body diagram. You want to put your positive coordinate directions. That's important too. Make sure you put the positions of the forces, the dimensions, in the positive coordinate directions. But we don't need to put the z-axis because we know it's part of the right-hand rule, so we know the z-axis is going to be out of the page. We use the right-hand rule, x to y, push x to y with the right hand. But, so yeah, you just put these in the positive directions. They're unknown forces. The final answer will tell you if you got these force directions right. If you get ax is equal to a negative number, then it's going to be that magnitude of that magnitude in the opposite direction of what you put. Okay, and just to point out a couple of things here. So let's say there is some contact, a point of contact between the bracket and something in the environment. So maybe this bracket is touching something that it shouldn't be touching, right? There's an unknown contact. So we don't know the magnitude of this force from the foot, but this foot is part of the system where we're familiar with this. Let's say there's you notice that, okay, this is contacting something, right? So you're trying to identify all of the forces and you look for where is this bracket in contact with anything, any other component, anything in its environment. And you notice there's some contact point, but you're unfamiliar with it. What do? Well, analyze it and see. I mean, do you know for sure if that contact, there's really no force there? But if you're not sure, then you'll have to put it as an unknown force. But also analyze it to see, do you at least know the direction of the force from that contact? So maybe it's an unknown magnitude, but you know the direction of that contact. And so, okay, well, just to give you an idea, if there's smooth contact, or I can even put it like, the bracket is straight, but so there's smooth contact, meaning the frictional forces are negligible between the two surfaces. Well, then the contact force is going to be normal to the surfaces. Well, we will remove this. The contact force if this is the free body diagram, will be normal to the surface. But if there is unknown friction force, then you might have to put an unknown force with an unknown theta, an angle as well. And so then the horizontal component would be the frictional force and the vertical component would be the normal force. Okay, and also you might say, well, what if this pin here is really rusted? And so you're pushing on the lever and this is these links are pulling back, but also this pin connection, that rust is all is also holding this link from twisting as well. Well, if that's the case, you could put an unknown couple moment. And remember, with free body diagrams, we only apply forces in couple moments. You don't apply like a moment about a point. It's only forces in couple moments. So you could apply a couple moment here, an unknown couple moment. But just note, we're going to talk about the different kinds of connections in a second. Ideally, like the nominal case, if you have a pin connection, there should be negligible, even the natural friction in the pin should be negligible compared to the forces, to where there is no couple moment here. It's purely preventing translation. There's the couple moment due to natural friction is negligible. If you've got such a rusted connection, well, you should go fix the connection. A proper pin connection doesn't support any significant moment. Okay, so there you go. There's an example of a free body diagram. Now, if you notice, though, the free body diagram we just did was a special case. This is a planar free body diagram, right? This is in 2 dimensions. So what are the requirements of the system that allow you to do a planar free body diagram? Well, if all of the forces are coplanar. No, that's not the requirement. In fact, the forces don't have to be coplanar. The requirement is that the geometry of the body that you want to make a free body diagram of needs to have a plane of symmetry through its center axis. And in addition to that, the second requirement is that all of the forces, known and unknown, need to be symmetric with respect to that center axis plane. And then third, all of the forces can't have any components that are perpendicular to the plane, that center plane of symmetry. And then actually, so we could say fourth is that if there's any couple moments, then the direction axis of the couple moment needs to be perpendicular to that center plane. If those requirements are met, then you can project all of the forces onto a single plane. And you can think about that plane as being the center plane, that symmetric center plane. So let's take a look here. How does this fulfill the requirements? Well, first of all, the bracket has a plane of symmetry that passes through its center axis, right? If you think about into and out of the page, the thickness of this link, it has a plane of symmetry down the center line. It's symmetric. Okay, and so thinking about the forces, well, if we were considering the weight, gravity, that's always going to be, you can put the weight of gravity acting at the center of mass. And gravity here would be acting, if we were considering the weight of the link as non-negligible force, that would be acting straight up and down in that center plane. It's not like this is that. It's not like this. The center plane is tilted here. It's straight up and down. But again, we're not even considering the weight of the link eligible here, so it doesn't matter. But okay, all other forces, non-body forces, we have to think about the area of contact, that load distribution. The load distribution needs to be symmetric with respect to that center plane. Well, let's think about the most general case here. So if we were doing like an extreme analysis, which again would be overkill for a statics problem, but if we modeled this, if we looked at this as the load distribution from the pin on this face, on the face inside of the pin, let's say it's parabolic. So in other words, the force from the pin on the face of this, we call it like a clevis on the face of the link inside this inside face, it's higher towards the center line of the circle here, and then it tapers off as you go away from that being in line with the center of the circle, right? Well, when we talked about coplanar distributed loads, to model a distributed load as coplanar, the requirement was that, so let's put this same parabolic distribution at this end. The requirement for a coplanar distributed load was that at each point on the distributed load curve, the pressure doesn't vary along the thickness. It's constant. That's the requirement. And if that's the case, then this is symmetrical with respect to the center plane of the link, right? This load distribution is symmetrical. But that's not a requirement for a planar free body diagram, because let's just say along the thickness, the load distribution was like this. So in other words, you get to a point under the distributed load curve, but then the pressure is also a function of the thickness direction. It's a function of it's three-dimensional. Well, it's three-dimensional in either, even if it's a uniformly distributed, but the pressure changes in all directions. Well, in this case, it would still be symmetrical with respect to the center plane, right? So you could still do a planar free body diagram like this in that case. Now, just so you understand this, the idea is, so again, every single contact force is going to have some area of contact. There's no such thing as a point force. There's always going to be, for all surface forces, there's some area of contact. For the load distribution, the idea is it's a pressure, it's a force per unit area. And for that area of contact, you can specify a point on that area. So here's the area of contact. You have that entire area of contact where the pin contacts. You have the area of contact. It's two-dimensional, right? Two-dimensional meaning you can model it to where you can give 2 dimensions and you can specify any point on that area. The idea is, with a pressure distribution, you give a point on that area, and then what comes out is a pressure value, right? So you have a total volume under the pressure curve. You can calculate the volume under any pressure curve. In the previous section, we calculated areas under pressure curves because it was a coplanar distributed load. It was a special case where we only had to consider the area under the curve, not the volume, because the thickness was constant and it was factored in to the distributed load curve. But in general, you're thinking about a volume underneath a pressure distribution. Even with the coplanar distributed loads, we're still in effect calculating the volume under the pressure curve. It's just we calculate the area and the volume is already factored in. The thickness is already factored in, so the volume kind of component is already factored in. The volume under the pressure curve is this load here, is 20 pounds in that pin, or it's 30 pounds here. And what happens is if you have a distributed load that's symmetric with respect to that center axis plane of symmetry, and also, so here's, let's say this is a pressure curve. There's no components that are components of the pressure that's perpendicular to that center plane. So the distributed load is symmetric with respect to the center plane, and there's no components of that pressure that's perpendicular to the center plane. Then the resultant force is going to lie in the center plane. And if that's the case for all of the forces on the free body diagram, then that's why you can do a planar free body diagram. It's like you're looking at that center plane. You're just projecting everything onto that center plane. All right, here's a planar free body diagram. Why does this free body diagram work? Well, you think about the plane, coming from this direction, it has a plane of symmetry, an axis of symmetry down the center of the plane. Right? The geometry of the plane. Just talking about the geometry of the plane. But we're not done satisfying the requirements. The loads, all of the loads. So we're going to get to this in a few minutes, but we're treating this entire plane as a free body, as a rigid body. The wheels, everything connected together. The entire plane is one free body, one connected free body. And we'll get to how that works in a few minutes. But if we factor in all of the loads that are acting on this plane, you got the body force, the weight, acting at the center of gravity. There's no electricity and magnetism. So the contact force is the only contact, the plane isn't moving, so there's no wind. The only contact forces are at the wheels here and this wheel in the front. Well, there's two wheels here, one on each side. But the wheels are symmetric, right? And in this scenario, the plane's just sitting there. It's a good assumption to say that the normal forces on both of the wheels are the same. This wheel is in the plane of symmetry. This one force is in the plane of symmetry. So there you go. The loads are symmetric, and there's no components of the loads that are normal to that plane of symmetry. And then there's no couple moments here, but if there were couple moments, the couple moments would have to be, the axis would be normal to the plane of symmetry. So there you go. You just project everything onto that plane of symmetry and do a planar free body diagram. They put 2T here because there's the force from both of the tires. You project all of those forces onto the plane of symmetry, right? Because those forces aren't coplanar. It's not a requirement that the forces be coplanar to do a planar free body diagram. Okay, you'll see a lot of examples of planar free body diagrams on vehicles. All vehicles have a plane of symmetry down the center. The geometry of the vehicle is symmetric with respect to this center plane. Okay, but are the loads symmetric with respect to that center plane? Well, okay, we've got vertical force, let's say on these on the two back tires, but there's also, let's say, like a traction force as well. And then we'll imagine we'll say this is not four-wheel drive, so there's no traction force on these tires, just a vertical force. You got the weight of the car at the center of gravity. Yeah, so it makes sense how just in general, a car driving in general, you can model it, do a free body diagram that's planar. Not every time. If the car's turning, then there's more traction on like this tire than this tire, let's say. So it's not symmetric then, but just a car driving straight, accelerating straight, or constant velocity straight, whatever, the loads are symmetric. And there's no component of these loads that's perpendicular to that center plane. So you can do a planar free body diagram. And so another way to think about this is, all right, so technically there's these areas of contact. There's a distributed load here on the tire, some sort of distributed load. There's a distributed load that's in the traction direction as well, and all in that area of contact between the ground and the tire, right? Same here, same with all the tires. Well, okay, we learned how we can take any force or couple moment system, and reduce that down to an equivalent force and couple moment. Well, if you have a case where you can do a planar free body diagram, the idea is, so if we took these back two tires and we reduced down these distributed loads and then combined the distributed loads here on this tire and this tire, we combined them all together and then found a resultant force and the location of that resultant force. The resultant force is going to be in the plane of symmetry. It's not going to have any component coming out of the plane of symmetry. It's going to be located at the center between the two tires. We talked about how you can have a force, you reduce a force, and that force actually is not even on the body itself. It's just a representation, right? The reduced force wouldn't be on any tire. It would be in the middle, but that's just a representation. That's the idea for a planar free body diagram. If you reduced all of the forces, point forces, distributed loads, couple moments, you reduced it all down, it would all fall into the center plane, the center plane of symmetry. That's why you can do a free body diagram projected onto that plane of symmetry. Okay, now you might be saying, well, wait, didn't we talk about coplanar force systems and how we could, those were special cases and we could reduce those down, right? We talked about this case, a coplanar force system, or even a parallel force system, or a concurrent force system. But for a coplanar force system, how can we have a case where there's a coplanar force system and we can't make a free body diagram on a plane? How does that work? Okay, imagine this. Imagine we have a plane that cuts through this car at an angle, right? It's not in, we could put an axis, coordinate axes. Well, no, we could put coordinate axes on this car. Like, let's say this is the X, this is the Y, and this is the Z. But this plane is not parallel to the X, Y, or Z. It just cuts across. And we had all kinds of forces in this plane. And that's it. That was the only forces on the vehicle. And maybe even a couple moment that the axis is perpendicular to the plane. That's the only forces on the vehicle. So yes, we could use the coplanar force special case to reduce all of these forces down to a single force in that plane. And we could also get rid of the couple moment, right, for the coplanar case. Just a single force. But, okay, so let me put the coordinate axes back here. That resultant force is going to be oriented in some random direction in 3D space. Inside the plane, but some random direction. Now, you could put a coordinate system that's inside that plane and just specify that force in 2 dimensions. So you've reduced down that entire force system to just 2 dimensions. But for a case like this, why would you do that? Because you want to see the forces relative to a coordinate system like this, right? The forward direction of the car. These coordinate directions make sense. You would want to represent that force with 3 components relative to these axes. I mean, that force oriented randomly like that could be causing the car to spin. That would be like a 3D case. So just because you have a coplanar forces doesn't mean that you're going to have a planar free body diagram unless those forces are in a plane of symmetry. Okay, so I mentioned that we could make a free body diagram out of, we could take any single component, so we took out this component, or a group of connected components. So what does that mean, a group of connected components? Well, before we look at this scenario, we need to go over the concept of a rigid body. Now, you might already know the definition of a rigid body, right? So a body that doesn't deform when a load is applied to it. But let's talk about the idea of a rigid body in a bit more detail so you can understand a few nuances that are associated with the idea of a rigid body. Okay, so yes, the definition of a rigid body is that you're assuming the body doesn't deform when load is applied to it. But first of all, note that there is no such thing as a rigid body. Every single body, solid, liquid, or gas, but we're talking about solids. Every single solid body will deform when any load is applied to it. So the stiffest known material in the universe, I believe, is diamond. If you squeeze a piece of diamond with your hand, it's deforming based on that squeeze load you're applying to it. So, okay, the idea of a rigid body is just that. So we're doing static analysis or dynamic analysis. Let's look at this link here. Before these loads are applied, the link has some shape, geometry. And then after the load is applied, the link pretty much has that same geometry. Technically, if you look at it from a zoomed-in standpoint, it doesn't. But the idea is that if we're assuming a rigid body, we're not going to say, well, technically, after you've applied the load, here's a deformed geometry. This has come down a little bit, right? This has come up a little bit, right? It's expanded out. And so the line of action of this force is changed ever so slightly. So we need to consider all that to get an accurate answer. That would be crazy. The assumption is that we don't have to think about how the lines of action of the applied forces are changing as a result of once the load is applied, as a result of the body changing shape. Now, this is just in rigid body mechanics, statics, dynamics, when we're solving for forces on all the different forces on a body. In deformable body mechanics, we'll get into the actual change in shape of the link and start studying the stresses in the material. But that's a different problem. Remember that these idealized assumptions that we use, the particle assumption, the concentrated force assumption, that's problem specific. Those assumptions are unique to each problem you're trying to solve. Okay, now you might say, all right, so we assume like metals or steels, for example, aluminum, those are rigid bodies, but rubber that's not a rigid body. That's incorrect. Remember, the assumptions are problem specific. If the loads I input here, the known loads are big enough, this is not going to be a rigid body. This will spread out and deform. So if the loads are big that I introduce into the problem, this piece of steel might not act as a rigid body. If I made a replica Bobcat out of rubber, like a toy replica, or even a toy Bobcat out of plastic, well, in that case, for the application of that toy, for what that toy is designed to do, it's designed to hold plastic loads, little plastic toy pieces, right? Well, it's the same thing. I mean, those pieces of plastic are rigid bodies for that design scenario. When you apply the load, when you lift up the plastic bucket and put a bunch of plastic Legos inside the bucket, do the components, do they change shape in any significant amount? No. You could assume that the shape of all of the load-carrying components in that toy is the same both before and after the load. That's a rigid body. I mean, even liquids are known to be highly incompressible. So you can think about when we get into free body diagrams on liquids, those are kind of like rigid bodies where all of the pressure forces don't change shape, but I don't want to confuse you. We'll talk about free body diagrams of gases and liquids and fluid mechanics. Okay? Now, another thing to think about is, let's say this piece here. Let's say it was made like this section over here was made of steel. This section over here was made of copper. This section over here was made of aluminum. And this section was made of tin. Well, let me not say tin. Tin's pretty flexible. Titanium. Now, I don't know. I don't know how you'd make a component like that with like these. I guess you have to weld those materials together. But this is just for illustration. I've never seen an actual component that has materials like, in sections like that, has metals like that. But let's say you did. Is that a rigid body? Well, the materials that something is made of makes no difference. That has no bearing on whether or not you're going to treat something as a rigid body. When the loads are applied to it, does it change shape? Does it change shape of any significant amount to where, again, like the idea would be, so we assume this force is vertical, right? We assume this force is horizontal. But if this was also all of a sudden changing shape too much, well then before the load, like right when these forces become taut, they're vertical and horizontal, but then you apply the load, this link changes shape, and now this force is pointing down. This force is pointing at an angle now. The problem's changed. That's what non-rigid bodies, that's the issue with a non-rigid body. Here, would that be the case? So with the different metals, would that be the case? No, it would be the same thing. It would be a stiff, rigid body. Now, if this was made of tins, like a tin can, tin is really, really soft compared to like steel. Well, in that case, if you're applying loads that like are typical of what steel would handle, well, then all of a sudden, then this would really bend like a tin can, and that's not a rigid body anymore. Or if this was made of rubber, if you had the middle part made of rubber, but everything else was made of metal. Well, if all of the load is going through the rubber, like if all of this was all rubber and you had everything else was steel and you had these full loads on here that the steel would carry. Well, because all that load has to travel through a pure cross-section of rubber, the whole thing would deform, right? So then all of the forces on the steel, all of these forces on the steel would change their orientation, so it's not a rigid body anymore. Okay, so now that you have a better understanding of the concept of a rigid body, let's think about two members that are connected and two rigid bodies that are connected. Two or more rigid bodies that are connected together, like bolted together or pinned together. Okay, so here, is this a rigid body? Think about you applying these forces here. Is this a rigid body? Well, right before you apply the load, or you just make it taut, like you put 1 pound of load. The body has a shape. Then you apply the full operating load or the max load or whatever. That shape doesn't change. These bolts are holding. It's still rigid. It's a rigid body, right? These bolts are holding it rigid in the sense that the shape doesn't change. So if you think about a skyscraper, now as far as the loads, what you want to think about is imagine stripping off all of the non-load carrying components, at least carrying the weight of the building, right? So these windows aren't all of the furniture and the people in the building. The windows aren't carrying any of that load, right? So imagine stripping down all of the windows, all of the skin, and just looking at the skeleton, which would be the beams, all the cross beams, all the vertical beams. That's what's carrying the load. Is the skeleton of this skyscraper, is that a rigid body as a unit? All of those pieces connected together, all of those connected pieces. Yes, because you could have a hurricane, you could have whatever. The shape isn't changing before and after you apply the load. The shape of the entire unit of connected members, right? So here's a connection. That's a rigid connection before and after you apply the load. So, let's say they started building the skyscraper and then they had this shape, and then they started adding the entire skyscraper material on top of it. So all that weight was on top of this, and then they added all kind of furniture and people. And then also at the same time, there's a big storm coming through. Is this shape changing? No. The lines of action of all of the applied forces, both before and after loading, are the same. Okay, here's a free body diagram that includes the entire engine and the chain. This chain that's lifting the engine. Well, that's confusing, right? Chains are flexible. Chains aren't rigid, are they? Remember, with free body diagrams, you're taking pictures, snapshots in time. Typically, something's in operation. It's in action mode. It's doing the thing it's designed to do, and you take a snapshot. It's either still or it's accelerating. You take a snapshot. So we've got this snapshot at this moment. Then you imagine you release this load just till it gets to like 1 pound of force on the chain here, to where it just gets to the tout position, right? If you go past that, then the chain's all floppy and the geometry changes, right? But just at the tout position. So there's pretty much no load. There's just barely enough load to make this tout. So it's unloaded. Then you lift up the engine. Does the geometry change of this chain triangle? No, right? Nothing changes. Nothing in this entire geometry changes. So the chain connected to the engine is a rigid body. The chain and the engine as a unit act as a rigid body. Now, you might be wondering, well, couldn't it looks like here, potentially, if I applied, a force like this, then these plates would rotate. I mean, maybe they wouldn't, depending on how tight the bolts are. If you come here, depending on how the force you apply to this beam, the beam, these two can rotate, right? There's a degree of freedom here. This beam and this plate here can rotate with respect to one another. Okay, well, if there is potential motion that is designed to be there, it's part of the design of the piece, then that axis of motion you're not including as acting as a rigid body, right? So this bolted plate is not designed to have any loads in this direction. If there were loads coming those directions, they would have a different design here. So we're looking at it from the standpoint of, for this direction of load, is this connection of two plates here as a unit, is that a rigid body? When you apply a force in that direction, does the geometry change in that direction? Right? So you think about the idea of rigid body on a direction by direction basis. But even more than that, so here, well, no, it's not a rigid body. This link here, you apply the force and it rotates. It rotates in this direction. Don't think about a rigid body that way, because yes, it's rotating, but the link is rotating with what's called rigid body motion. What does that mean? That means that, yes, it's moving, but what's not changing is like the relative distance or the distance between these 2 points. The only way the distance between these 2 points would change is if this part was made of rubber and then it started deforming in this direction. Then the distance between those 2 points would change. But if this is just rotating about this pinpoint here, then it's rigid body motion, which if that's happening, then that's typically going to be part of the design of the piece. Like piece is designed to rotate like that. And so like what would happen is we took a snapshot of this link whenever it was in a still position. That's the assumption. It's in the still position. Where the foot's pressing down, it's stopped. We took a snapshot and we're doing a free body diagram. But let's say hypothetically you had someone push their foot as hard as possible and then release it fast. And we took a snapshot whenever it was like the link was and it was accelerating. Well, it's still rigid body motion. It's accelerating as a rigid body. Again, the relative locations between points aren't changing. But in dynamics, what we would do is we would still put all of the known and unknown forces, but we would also specify that this has an acceleration, and it would just have a rotational acceleration, not a linear one. Why? Because this pin here prevents any translational motion. As far as translation goes, this is acting as a rigid body. But rotation, we would specify, if we knew it was accelerating, we would specify, okay, there's an acceleration, angular acceleration. And then we'd use Newton's law, but with the acceleration wouldn't be equal to zero. We'd use the Newton's laws with moments and angular acceleration, Newton's second law. And sometimes you need to consider the dynamic load cases. Sometimes the dynamic load cases is what could cause something to break, right? What if somebody presses real hard on this and they keep releasing it and they don't release it slowly? Maybe that results in much higher pin forces than just the static fully pushed in case. You might have to look at that. Okay, now if you look closely here at this free body diagram, and this looks to be a planar free body diagram, but I imagine the chain is wrapped all the way around and then loops back up here on both sides, so it's symmetrical. But you've got like 4 total chain forces, 2 in the front, 2 in the back. But if you look closely here, it looks like they've made an imaginary slice in the chains and then applied forces to the chains at those imaginary slices. That's something that you can do to make a free body diagram. So like I could, for this beam here, looks like these pieces are welded to the beam. I could remove the beam, this beam here. I could remove the beam fictitiously, like bring it into empty space. It's bolted here to this vertical beam, and then it's bolted at these plates that are welded to it on these angled beams. I could remove those connection points. And then, as we talked about, those are points where this beam was contacting something in its environment. So those are contact points. And so I put forces there. And we talked about this before, but we're going to get into this in a second. But you can imagine these connections here, these bolted connections, don't support any rotation. They aren't preventing this beam and this beam from rotating relative to one another. You might say, well, oh, there's friction there. When you're talking about the enormous weight of the skyscraper or whatever this is and all the furniture on it, the friction force is nothing, is negligible compared to the translational forces that are in the connection. This bolt is preventing any translation, but it's not preventing this, right? And it's not supporting any rotation, preventing rotation. Rotation between these two connected members. These are the two pieces that are connected. What if they wanted to, they could translate, this could move out here, this could move out here, they could translate, the bolts are stopping that. But what if they didn't want to translate, this just wanted to rotate, and this wants to rotate here? Well, it can't do that because it's also bolted at the other end, but if you unbolted it at the other end, and unbolted this at the other end, then there'd be some friction, but you could rotate them based on this connection. You could change this angle without doing any translating. Okay, but one thing I can also do, again, I could remove this beam here, move it into empty space by taking it off how it's connected to other pieces, or I could make a cut in the beam, an imaginary cut, a plane. Right, so if we come here, imagine this is the bolted end. So this is fixed. That's this end of this beam. And let's just say, hypothetically, we unbolted the other end. So this is a free end. And let's imagine there's a load here. Okay, so we could imagine unbolting this end. This end is free. And then bringing the beam into empty space. That's what we've already done so far. But this time, let's imagine instead we make an imaginary cut. Through the beam, anywhere along the beam here. And so now what I'm going to do is imagine that, so we make this cut, and we bring from the cut to the free end into empty space. So we erase all of this end, and now let's imagine that now we're zoomed in on the beam. Here's that cut. We can't see the end that was bolted. This is the cut end. This is the cut. This is inside the material. And here's the force. But we could have any forces over here. And again, this is a free end. Okay, so remember the process is we remove a component or a group of connected components. We haven't talked about connected components yet, and bring it into empty space. We remove the component either by undoing connections, so bolted connections or any kind of connection, undoing where the member or group of connected members are connected, and then bringing that body into empty space. Or we have the option of making a cut through the material. Or you could have a mixture of both. You could remove some connections and then do a cut at another location, so you could have removed connection points as well as a cut. Now, we made the cut, so we're coming back to the original image. Here's the bolted end. Here's the force. We made the cut somewhere along here with a plane. And the plane was perpendicular to the axis of the beam. But we can make any cut we want. The plane could be at an angle from the axis of the beam. It doesn't have to be a plane. It could be a wavy surface. So you would have a resulting cut with this wavy surface. You can make any cut you want at any location you want. But okay, what did we do before? Once we had our component in empty space, we applied all of the body forces. So we can go ahead and apply the weight here. Why not? Maybe it's negligible with beams. Sometimes the loads on the beams are so large, the weight of the beam doesn't matter, but let's apply it. We put it at the center of mass of our cut section, right? We're just dealing, it's not the entire beam, just the center of this cut section here. The weight is just the weight of this cut section, just the body that we brought into space. All right, so there's no electricity and magnetism to deal with here. So then we look for what? We look for points of contact between the beam and its surroundings. Well, we're not imagining that this was unbolted. We're just treating this as a free end with a force here. There's a contact here, so we put that point load because the area of contact is small relative to the entire beam, so we have this point load here. There's no other areas of contact or points of contact anywhere on the beam. But what about this, where we cut? This is a little different. This is not a bolted connection. There's no regions where a bolt was contacting the beam or something, some sort of connection was contacting the beam. Is there contact here? Yes, there's contact. Contact between the material in this face and then the corresponding material that was on the opposite side. The area of contact is this entire cross-section. Okay, so what's the process we did? We identified points of contact or areas of contact, and then we looked to see, is that area, the size of that area, large relative to the dimensions of the body? Well, yeah, this is large relative to the dimensions of the body, because the idea is, if this is a small area of contact. So we just put the arrow at the center. We make a point load at the center. But if we made it off center, it wouldn't really matter, right? If we made it a little bit off center, it wouldn't matter anyway. But here, we could put a resultant load, let's say this in this direction, at the center of this area. But if we moved it off center, say here, that's going to make a difference, right? This is the entire length of one dimension of the beam, of the entire beam. So the size of the area is not insignificant. And if we look here, let's say we made a cut here. So we removed all of this. We made a cut here. We removed all of this. Well, let me put it. A cut here and removed all of this. Is the size of the area negligible? No, it's not negligible, because if you could put the resultant force here, but you could maybe put it here or here. I mean, it is pretty small, but it's like saying, well, then I could put this force here or here, this 30-pound force. Well, no, you can't. You need to know where it's at. It's only if the area is like, this is the contact area, the surface of the hole. So you could put the force here or here. Well, that's pretty much the same thing. So you'll put it at the center. You just assume a point force. Because if you think about it, that's what you're doing anyway. Like if you have a distributed load, if this is a distributed load, to do the static analysis, you're reducing the distributed load down to a single point force anyway, and then doing the analysis. It's just with a distributed load, it might be the case that the resultant force is not at the center of the distributed load, right? That's what you're doing when you assume a concentrated force. You're just putting the force at the center of the load distribution. But if you have a distributed load, it might be the case that you can't put it at the center of the load of the area, of the contact area. It's going to be off center. And so if the area is large, you have to consider, well, maybe the resultant force is going to be off center. And since the area is large relative to the whole body, that would make a difference. That off center position would make a difference. Okay, now, so this is a point of contact. There is some load distribution here, right? A pressure distribution. You specify, you give two dimensions, which gives you a point on this surface, and then output is a pressure value. That's what there's some sort of pressure distribution here, and the volume under that curve, that pressure under that pressure curve, pressure surface, is the net resultant force. And then if you do the moments of area or moments of volume, you can get the location of the resultant force. But what's the pressure distribution? Well, okay, the first thing to think about is when we're doing the free body diagram. Well, actually, let me put let's put the forces back. There we go. So when we're doing a free body diagram and we're analyzing the contact forces, so we find a point of contact, so we know there's a force there. One thing we look at is, so let's come back here. Here's a point of contact. Here's the link, and we know we have a point of contact here between the pin and the link. The pin's not part of our free body diagram, so we know that there's a point of contact here. Once we find a point of contact and we know there's a force there, we then analyze what kind of motion is that force preventing the body from doing. What kind of motion is that force preventing the body from doing or causing the body to do? You can think about it that way as well. But with a connection like this, like we'll talk about the difference between like a connection, a reaction, and an external force. With a connection like this, it's more about what's that connection preventing the body from doing? How is it constraining the body, right? Like external force like this is more about what is it causing the body to do? Well, okay, here the pin is preventing the link from translating in the X or Y direction. And you could say, well, isn't it preventing it from translating in the Z direction? Yes, technically yes, but a connection like this isn't designed to be holding any significant loads in that direction. If there's any significant loads into or out of in this direction, into or out of the page or in front of or behind the pin, then that's not the right connection. You need a different kind of connection. There should be no significant loads in this direction. The pin is nominally, it's preventing the link from translating in the X or Y direction. And it's not preventing the link from rotating in the Z direction, about the Z axis. So the only thing that this pin is preventing is translation in the X or Y direction. And the same idea, you say, well, it's preventing rotating about the X axis or the Y axis. It's not designed to do that. There should not be any significant couple moment preventing it from rotating about the X axis or the Y axis. If that's the case, then you need a different connection. Okay, so since this connection here, this surface here, is preventing the link to translate in the X and Y direction, we put forces in the X and Y direction, and we don't put a couple moment. Okay, so here's our cut surface. We have a point of contact here. We know there's some sort of load distribution here, but okay, the material, the contacting material right adjacent to this that we removed. What is that preventing the body from doing? Well, it's preventing the body from translating in the X, Y, or Z direction, and it's also preventing the body from rotating in any direction as well. It's a full constraint. It's constraining it from all types of rotation and all types of translation. That's the way you think about it. So in general 3D, you've got X, Y, Z. So you could have translation in the X, translation in the Y, translation in the Z, or rotation about the X, rotation about the Y, rotation about the Z. And the corresponding forces, you have like a force in the X, force in the Y, force in the Z, or couple moment in the X, couple moment in the Y, couple moment in the Z. That's the most general way you think about the way something can be constrained, and the corresponding forces, the forces or couple moments that correspond to that constraint. Okay, so with that in mind, we know that there are potential resultants. So the resultant under the load distribution, there's a resultant force. Force is preventing this from translating and rotating. Now, we could put a force in the Z direction, a couple moment about, preventing it from rotating about this axis. But if we look at our loads here, this is a planar problem. So we're only going to think about, okay, translation is being prevented in this direction, and rotation is being prevented about this axis. So rotation is being prevented in this direction. Everything else is we could put those other reaction forces, but they're going to be zero. This is a planar problem, a planar free body diagram. Okay, so again, somewhere on this surface, if you got the volume under the pressure distribution curve, you have a resultant force preventing translation in this direction, preventing translation in this direction, and then a resultant couple moment, not moment, couple moment, preventing rotation in this direction, rotation about this axis. Okay, so we could just go ahead and put those forces, right? They're unknown forces, let's say. Only issue is, where do we put them? Where is their point of action, right? We could get the volume under the pressure distribution curve, but then what about the moment of volume, you could say, like, the moment of volume divided by the total volume, where you can get the locations of those resultant forces. Where are they going to be located? Well, okay, mechanics of materials is where you really get into this topic in detail. You're making cuts in members and analyzing the different pressure distributions and the locations of resultant loads that result from like bending or twisting or axial load or shear. You really get into that in detail. But for this course and for this video, just so we can get an introduction to free body diagrams, we're going to put all of the reaction forces, the tails of the reaction forces, at the centroid of the area of the cross section that we cut. And for the vast majority of problems, if not all problems in this course, it's going to be like we made a cut with a plane that's perpendicular to the axis of the member. The member is going to have some sort of symmetrical axis to it most of the time. Again, when you get to like mechanics of materials, you'll get into more detailed analysis of this. And sometimes there might be potential that the resultant force is not at the centroid of the cross-sectional area. A lot of times it is, though. Most of the time it is for most engineering problems. But like, okay, if we look here at this component, if we made a cut here, and then we took these connections off, made a cut here and brought that into empty space. Well, there's no like axis, right? There's no axis of the component. Like the beam has this symmetric axis here, but there's no axis here. And then also it's not like the cross-sectional area is constant as you go through this component, right? It's like this is some weird shape. The shape is changing. But even then, if you were just doing a basic analysis of this, you would look at the cut surface and say, how is this constrained? Well, you're cutting through the material, so it constrains in every way, right? Like a metal to metal contact, it doesn't allow motion in any direction. But you would say, okay, well, it's a planar problem though, so I don't have to put reactions, out of the plane or whatever. Or maybe it's not a planar problem. So maybe you put all 6 reactions, all 3 translations, all 3 couple moments. But just for basic analysis, you could put those forces at the center of the area. I mean, it's not going to be that wrong. But when you get into more advanced courses, so in mechanics of materials, most of the shapes that you study are these standard shapes, like an I-beam or a rectangular plate, right? The cross sections are like a square or a rectangle or a symmetric cross section, or like torsion on a circular shaft or a hollowed circular shaft. So it has an inner radius and an outer radius. That's not what this is, right? This is kind of an irregular shape. But when you get to even more advanced classes, like there's that book, Rourke's Formulas for Stress and Strain. It's this big reference book that allows you to determine the stresses and strains and pressure distributions on more irregular shapes. So you could, once you get to more advanced classes, you could find what the pressure distribution on something on this kind of cut would be. Now, I mean, to get even more general, what if you made a cut with a plane at an angle through here, not like normal to the thickness or in line with the thickness of the beam, or you did some curved cut. So you got some curved surface cut. Well, it would be the same idea. There's going to be some pressure distribution on that curved cut. I mean, this would be really complicated. I don't know why you'd ever do this, but I'm just I think it's helpful to study things, even the most general scenarios, even if you're never going to do those general scenarios, just to have that in the back of your mind. To me, that always gave me more confidence that, I'm not going to do that, but I have an idea of the direction I would go if I would do it. Or I could at least describe why it's impossible. If it is impossible or just ridiculous to do it, I can at least describe why accurately. So I'm at least aware of it. To me, that gave me more confidence. But if you did like a curved surface like that, I don't even know if that's in Rourke's Formulas for Stress and Strain. You could do, like an FEA analysis. Yeah, you do like an FEA and get an idea of the load distribution. You could do that. But coming back to this beam here, so in statics, in this introductory course, anytime we make a cut, we're going to assume that we have a pressure distribution that has resultant forces that are at the center of the centroid of that area of that cut. Okay, now usually it's going to be an unknown force, and with unknown forces you can put them in any direction, right? Well, the sense doesn't matter. So we have, this is the y-axis perpendicular to the beam. This is the x-axis along the axis of the beam, and let's say this is the z-axis. So y, x, z. We put a force, let's just put it in the positive y direction. But we could put it in negative, it doesn't matter. The sense doesn't matter. So that's what the translation that is being prevented. We have a force in the positive x direction, We're not gonna do any Z force. And then we have a couple moment, and we'll put that in the positive Z direction, so that would be this direction. So the couple moment is here. This is MZ. And there you go. So now we've represented the forces from this point of contact here, this entire surface. They're unknown forces. Now, okay, so let's draw the planar free body diagram. So it would be, here's the weight, here's this force, and then we'd have like that. And then you put the dimensions. You should put dimensions in the free body diagram as well, right? You definitely want to put this dimension, because this is based on the location of where you cut from the free end. And you want to show that these are in line here. Okay, now, when we made a cut like this, and we put these forces, these are called internal forces. Why are they called internal forces? Well, you can think about it. One reason is, what you do in mechanics of materials is you make cuts like that in pieces. You solve for these forces, in these pressure distributions. And so you're analyzing the forces internal to the member, right? What's going on inside? You call it stresses, the force per unit area, the stresses and the strains, the deformations inside of the material, internal to the material. But another reason they're called internal forces, and this reason, this kind of definition is more important to the free body diagram, is, okay, this is the original beam. It's bolted here. It's that bolted end, this end. And let's just say this is still a free end, and we've got a force here. And so we made our plane, the cut we made was somewhere around here. Well, okay, if we did a free body diagram, we just unbolted, we didn't make a cut, we just unbolted this here and then brought the entire beam into empty space. We added the forces from the bolts, and we continued to analyze, look for points of contact. Well, what about the forces in that plane there? Where did those go? Don't we need to add those? Don't we need to, on our free body diagram, so we add the bolt forces, don't we need to also add those forces right there? No, because for this free body diagram, those forces are internal forces. And so from that standpoint, you could kind of look at it like, for this free body diagram, these aren't internal forces anymore. These are more external forces, right? At least for this free body diagram. Here, those are internal forces. And internal forces in a free body diagram, you don't put those in the free body diagram, because here, we made that cut before, and we removed that adjoining face. Now that adjoining face is part of this. So at this point, yeah, you do have, these forces are still present on that face. But now the other face is part of the free body diagram, and it's Newton's third law. The other face is experiencing the exact same forces, but in the opposite direction. So they cancel each other out. Again, those forces are definitely still present. These forces are still there in this free body diagram, but now we also have the other face. We don't have that other face, right? Now we do. And with Newton's third law, for every action, there's an equal and opposite reaction. The other face has these exact same forces, but in the opposite direction. So they cancel each other out, and we don't put them. There's actually a weight here. Forgot about the weight. Okay, now it's important to understand this definition of internal forces, when they cancel each other out in a free body diagram and you don't put them, because, okay, I've mentioned several times that to do a free body diagram, you can bring, like let's say from this Bobcat, you could bring one single component into empty space, or two or more connected components. Let's think about the idea of two or more connected components. Let's say we're going to bring, this is connected somewhere down here, and we're going to bring this entire piece. These, it looks like two connected pieces into empty space. So let's do, it's kind of hard to see because this is white on a white background, but so this is like connected here. And then we'd undo this connection. So this would be a free connection, this would be free, this would be free. We undo the connection here, here, and here, and leave this connection. Okay, well, I've talked about how this is a rigid body. We're considering this entire assembly here a rigid body, one rigid body. I mean, as we've talked about, at least in the connections where it's rigid, like, yeah, this can pivot, but we talked about how to think about that. Okay, so we put the weight, if we're going to put the weight, we look for areas of contact. So we put like a, force here, here. Looks like there's no, these are like pin connections. There's no rotation being constrained. We'll say this is planar. We're not worrying about, forces into or out of the page or moments in those directions. But, okay, there's a pin here though, right? So I think it always made sense to me that, yeah, we're not going to include, if we could make a cut, cut a plane here. But now that we don't have a cut here, we're not going to put all these reaction forces inside the material, right? Because if I'm going to do that, well, then I can put the reaction forces here and here and here and here and here. It does, that doesn't make any sense. But there's a pin here, right? Don't we need to there's forces in that pin, right? No, the forces in this pin are internal forces as well. This is a rigid connection. We talked about how this is a rigid connection, how you can have a bolted plate or two bodies that are connected rigidly. And so if you have multiple bodies connected rigidly, but you didn't undo those connections, then those connections are internal forces. And so the way to think about this, you might find this confusing. Well, how do I identify what's like a connection that's internal forces in a body and what's not internal forces? When you're looking for areas of contact, that area needs to be exposed. If it's not exposed, then it's going to be internal. So here, this area is exposed. It's exposed to the surroundings. That's what we're looking at. We're looking at the entire area of this beam that we brought into space, and all the exposed area. Is there contact in any exposed area? Then there's a force there, right? Or you look for, there's also body forces, but we're talking about contact forces at the moment. Here, that plane, let's say we made that cut right here, but now that's not that area is not exposed anymore. So that's not a potential area of contact. Okay? Again, here, these areas inside these holes are exposed. Is there an exposed area here? No. Okay, here's a planar free body diagram. So the geometry and the loads are symmetrical with respect to the center plane of these shears here, right? The shears are symmetrical with respect to a center plane, and the loads are symmetrical as well. Someone's pressing on the shears to cut this piece of this twig. Are these all of the forces? Well, let's look at all of the exposed area. Is there any other area, exposed area that's contacting something in the environment? Well, the hands here, and so that's what they put these two forces, the hands. But what else? Okay, we've got these pins here, but these are all rigid connections. But there's no exposed surface. There's nothing exposed here, or maybe here, right? Well, with the twig there's nothing exposed. Like the shear blades are contacting the twig, but that's not exposed. So this is it. This is the free body diagram for this. We brought this assembly of components. We brought all of these components as a unit. They're all this is connected. This is connected. These are all rigid connections. The blade here, at least at this snapshot in time, this is like a rigid connection. The blade and the twig. We brought this entire assembly of components into empty space. We look at for all the exposed surfaces and apply the proper forces there. If it's not exposed, it's an internal force. Now you might be asking, well, look at all of these exposed surfaces. These are all exposed, right? Well, okay, let's remove the forces here. So we take a snapshot in time when someone is pressing down on the handles, starting to shear this twig. Effectively, there is no acceleration or velocity. It's like it's in that shearing process. So let's say there's no velocity or acceleration to deal with. So we bring this entire assembly here into empty space, including the twig. Now, that might be confusing. How is it including the twig? That's a rigid connection. At least at this snapshot in time it is, right? Right at this point when you're shearing, it's a rigid, this entire unit is a rigid body. You can apply forces of the magnitude of like a hand pushing down, and the geometry doesn't change. So you can bring this entire assembly, the twig plus the shears, into empty space. Now that it's in empty space, again, remember, when we bring it into empty space, there's no forces whatsoever. We've just taken it out of where it's at and brought it into empty space, removed it from its environment. Now we look at all the exposed surfaces. So these are all exposed surfaces. Where on these exposed surfaces was there contact? Whenever it was in its environment, at the snapshot picture, where was there contact with the environment? Well, here, between the hands. So we put those two forces there, okay? Now there's a lot more exposed surface, right? There's all kinds of exposed surface. Was there contact with the environment in any of these exposed surfaces? Yes, the air, but air forces are negligible here. It's not a hurricane or anything. Any contact of relevance, that where a significant force would result? No, right? Well, there's contact here with the twig. That's not exposed. That's an internal force. So this is the free body diagram of this assembly of components. This is the entire free body diagram. That's it. This force is acting down. This force is acting up. It's along the same line of action. So there is no net force on this whatsoever. That's why it's not moving. Yes, it's cutting. There's internal forces here, but this is not accelerating or anything. The net force is zero. Now, the way this problem is given, they also want us to look at, so we make a free body diagram of this entire assembly, but you remove the twig, right? So we could remove the twig and just bring this at this same snapshot, though. The snapshot in time is the same. Okay, well now here, if we look at all the exposed surfaces, here's two exposed surfaces, but we know there's forces on them. So we're assuming there's no like friction, let's say, so it's a smooth contact. So a force normal to that blade and a force normal to that blade. And we put the direction because we know the direction, we should know the direction of the angle of this blade, so we know the angle of this force. So now, without the twig, this is the free body diagram, these two forces and these two forces. Let's come back to the skyscraper example. So again, what you want to do is for any load analysis or structural analysis of some system, you want to think about the skeleton. The skeleton is where all of the main loads are traveling through. So in other words, this looks to be aesthetic. All this white here, it kind of looks like that's load bearing, but to me, it's probably only bearing the load of the weight of what's on top of it here, of the aesthetic piece. This is not part of the skeleton. Imagine taking off all of the windows, the walls, and getting down to just the bare bones. That would be, like a beam skeleton. That's what's carrying all of the load. The load being, so you've taken off all the aesthetic pieces, but now put everything back. So all the concrete floor, put the concrete floor back in for each floor. Put all the furniture back in. Put everything back in. All of the people. And then maybe it's a very stormy day, so there's wind. That structural beam, steel beam skeleton, that's what's carrying all that load. All that load goes through the skeleton, and eventually the beam structure is connected to the ground. So you can think about loads, it's kind of like electricity. It has to go to ground. The load will find its way to ground. The earth, at the end of the day, the earth is supporting the load of everything. Now, you wouldn't think about ground as earth in all circumstances. So let's say there was a floor here that had high ceilings, and then there was a machine shop on one of these floors, and there was a big pump or something in the machine shop, a big machine, a big drill. Well, ground in that case would just be the concrete floor in the machine shop. The ground floor of the building, the concrete floor of the machine shop, is infinitely stiff compared to the pump or the drill. Just like the earth is infinitely stiff compared to the skyscraper. Now, I'm not a civil engineer. I know the ground can actually, certain types of soil can move, but you get the idea. The earth itself is rigid, you could say. The earth in general, you could say, is rigid compared to the skyscraper. The concrete floor of a machine shop is rigid compared to the pump or the drill. So you've got the skeleton in your mind. Now put all the aesthetic stuff back. All the people, put everything back in, but you still got the skeleton in mind, and bring that into empty space. And again, I'm saying empty space. I'm not just saying bring it into the air here, because we want to get away from Earth too. Okay, so you can imagine it's suspended in empty space, the whole structure. You're really thinking about the skeleton. Okay, now let's put the forces, body forces. You think about the entire weight with everything in it, all the windows, the people, just the weight of it. Furniture, the entire weight of it. It's going to have a center of mass. Okay, so we put the weight at the center of mass, and now you can imagine, now let's just, for visualization, take off all the aesthetic stuff and just see the skeleton. We've got the weight applied. Again, because what's carrying the load is the structure. Yes, the concrete floors carry the load of the furniture and stuff, but let's just think about we're looking at the free body diagram of just the structure. So we've got the weight applied to it. There's no other body forces, electricity or magnetism. Okay, surface forces. Well, we can think about wind. So we could put some sort of distributed load, however we want, or maybe it would be like, you could get into a complex analysis of that, find the worst case scenario wind loading. Okay, but this was always confusing to me because it seemed like, man, you've got this whole structure as a free body diagram. This has to be a really complex free body diagram this is going to take a while to make. Well, remember, all of the connected components, all of these connections, they're rigid. These are internal forces, right? We can ignore these forces in the free body diagram. As long as we brought those connections with us, we didn't remove those connections, there's no exposed surfaces here. The only exposed surfaces outside of the wind force, right? There's contact between the wind and the steel structure. The only other exposed surfaces are going to be where we removed whatever was connecting the steel structure to the ground. So for example, you can think about it like, so let's say this is the whole skyscraper. I've taken out everything that's not carrying the main load, but we can imagine all the concrete floors are back in, all of the furniture is back in, all the people, the wind load. So you could put at the center of gravity, put the entire weight. Then you could put a wind load. This would extend like in 3D. Okay, but where else are there exposed surfaces that are in contact with something? There's no contact anywhere. Yes, the concrete floors would be contacting the beams, but we've represented all of that as a net weight acting at the center of gravity. So outside of areas of contact that are associated with this weight here, where else is there exposed surfaces that are in contact with something in the environment? Well, here, and here. And I'm not a civil engineer. I don't know. Maybe they've got more points that go into the ground than just 4 points, but this is just for illustration. So just for illustration, imagine this is one of the legs that's connected to the ground. I imagine the beams at the bottom would be large compared to the beams are very large in cross section as they get towards the bottom, and then as you go further up, the beams get smaller. But these go into the ground, so this is like a like a footing. I think they call this a footing. These pieces that go into the ground, depending on how big the building is, I think it's something like, that depends on how deep they go. Like this goes all the way to bedrock. I'm not a civil engineer. Again, this is for illustration. But you can imagine that. So at each one of these locations, let's say there's only 4 locations that are going into the ground that are supporting the structure. Well, you could unbolt it and remove it, or you could make a cut here and remove it. You could do whatever you want. But let's say you unbolted it, for example. You would have bolt force, bolt force, bolt force, bolt force. And that's the free body diagram. That's it. Those are the only contact points between the structure and the environment. These are all these other forces are internal forces. That's it. It's that simple. It seems like, how could it possibly be that simple? This huge structure with hundreds of beams. It's this enormous skyscraper. This would be the free body diagram for that scenario. If you unbolted the beams at the base like we just showed, that's the only contact points between exposed surfaces and the surroundings. That's it. If we made a cut like this at each of those beams, then at each point, the resistance to motion would be 3 forces and 3 moments. Right? Because these bolt forces can't resist moments. They can only resist translation. But the net effect is of all this, there's 4 bolt forces here, then there's 4 bolt forces at the other beam, so there's 16 total bolt forces. As a group, they resist moment, the moment. They don't allow the building to tilt. But the way you represent the forces, you don't put moments there. And actually, the bolts would resist. If it was the bolts, you would have for each bolt, you could put a force in 3 forces. I don't know what I was putting there. Yeah, for each bolt, you would put 3 translational forces. So I got that wrong. Technically, each bolt is resisting translation in all 3 directions. Now, there might be some symmetry, or it might be like a planar problem to where you could omit one of those directions, but hypothetically, they're resisting forces. They could be resisting significant forces in all directions. You have to analyze it. If a force in a certain direction would be negligible compared to the other forces, then you could omit one of those 3 translational forces. I don't design buildings, right? So I did that wrong. You hypothetically, for each bolt, you would have 3 forces. And then you go all the way around. Definitely a vertical force. And I guess with any wind force, it could be, all 3 forces at each bolt. But what you can also imagine, though, is getting the machining tolerances as accurate as you can is important, because if you don't drill a hole at the right location and you put all your bolts down and you have one bolt that's butted up against the surface while the other bolts are more loosely, or more there's more of an area between the bolt hole and the bolt. Well, then that bolt that's more butted up against the surface is going to take more of the load. It's not, because ideally you want to make sure that the machining tolerances are exact. That would be ideal. You can't do that. So that all these forces are distributed evenly amongst all the bolts. But if you do the machining wrong and one hole starts off smushed up against the bolt while the other holes are more in the center, well, that bolt's going to take all the load, and it could screw up. See, they're going to have to be going component by component, pull out just this beam and these 2 beams and analyze it, right? And I'm sure it's very complex. Analyze that free body diagram, get all the loads, make sure all the loads everywhere are sufficient. But I'm saying doing a general free body diagram on the entire structure, you might think the entire structure, that's going to be so complex. Not really. Okay, so back to the car. As it sits right now, if we bring the car into empty space, well, is that a rigid body, the car with the tires and everything? You could model it that way. Yeah, the tires kind of deform. I guess there's springs on the tires, so the tires come in a little bit, the rubber deforms. But in general, when you go from loaded to or unloaded to loaded, does the lines of action of the forces change? Does the whole configuration change? Does the car bend out of shape? No. Okay, so it's in empty space. Again, think about the skeleton of the car. The skeleton is what's holding the weight of the engine, the weight of all the aesthetic stuff, the weight of the seats, the person. And then all that load is transferred through the tires to ground. But you put all the aesthetic stuff back on, the seats and everything, the skin, find the center of gravity, put the entire weight at the center of gravity. What's next? There's no electricity and magnetism. That's all the body forces. What are the exposed surfaces that are in contact with something in the environment? Well, the car's parked. We can neglect wind. Maybe there's a slight wind, but that's negligible. The only point of contact is between the wheels and the ground. That's it. It's that simple. It's deceiving, right? It's the entire car. It's a rigid body. I mean, you could even, let's even think about, so the car's driving. In that case, you have to factor in the wind, so you have to apply some wind load. You could still do like a 2D problem. If it was just driving in a straight line, you could do a 2D problem. But you could do some simplified model of a wind load. So that's contact on the car, but then still the only points of contact are between the wheel and the ground. After that, after the wind, the only points of contact, if the car is moving, is between the wheels and the ground. The weight of the car and the traction. That's the free body diagram. That's the entire free body diagram. We don't have to put the internal forces in the connections. Okay, so you can see how you can do a free body diagram on like an entire system like that. You see, and you see how simple it can be. Even though you're doing it on the entire system, it can be, it's that simple. But again, but in design, you're going to be taking out all kinds of assemblies of components. We talked about how we could just do a free body diagram here on this assembly of components, right? So you can get the size that this pin needs to be, the size that this pin needs to be, the size that this pin needs to be. Okay, take a picture here, take a snapshot. Let's say it's not moving, it's not accelerating. Maybe we want to take the bucket. We're going to take this assembly of components into empty space. So okay, so but we would these pins would be gone. We remove those connections. So this is just these are open holes. Okay, but this pin here, this pin here, this pin here, that's internal forces. So we would get this is the center of mass of the bucket, I believe, but you would get the entire center of mass of all of this, and I guess it would be something like, it could be here, let's say. And then you'd put, these are pin connections. All of this other stuff is internal forces. Just make sure you put for a free body diagram, you put your coordinate directions and you have to put the dimensions too, right? So you have an entire machine. There's all kinds of free body diagrams you could do. And again, mainly with the skeleton, the structural part that you're designing to carry load, significant load, to where you want to see if the components are going to break or not. In other words, this metal plate here is not load carrying. That's just a cover for the backside. That's probably just sheet metal, right? So you could do a free body diagram on this entire machine like it's shown here. And chains and slings always would confuse me because they're not rigid. But remember, the idea is like we could make a cut here and then make a free body diagram just out of this. You would neglect the weight of the chain, of the sling, put the weight of this beam, this concrete beam here at the center of mass. And the idea is, if you just made this close to slack, there's only like 5 pounds, you'd have this geometry of sling and concrete beam, right? Then once you lift the beam fully, you'd have that same geometry. It's a rigid body. So you do this free body diagram, you find the force here, then you come back and you do another free body where you make a cut here and remove all of this, and you have a force, that force that you saw on the rope or on this, whatever this is, this chain, or I guess wire rope. Well, this is a rigid body. All of this going through the wheels to the ground, right? Think about the skeleton. If you make this slack and then you apply the load, the geometry doesn't change. And all of those all that load going through the skeleton doesn't matter. It's all internal forces. So all you have to look at is the loads in the wheels going to ground. That's the only contact points, unless there's wind. Well, also then you include like the weight, whatever the center of mass would be of everything. Maybe that's here, of all of the structure. Again, this is a rigid body. The chain combined with the engine. The chain is like wrapped around, you can imagine, wrapped under and around. But if you put the engine on the ground and just release the load slightly till there's like 5 pounds in the chain, it has this configuration. Then you lift up the engine and it has that same configuration. Now let's imagine that the engine is swinging. So for any free body diagram, even if it's a dynamic case, if the body is accelerating, the rigid body is accelerating, you take a snapshot at a moment, bring the body into empty space, but specify what the acceleration is of the rigid body. It's going to be moving, but it's going to be rigid body motion. You specify the acceleration as a vector, the acceleration vector in 3D, or if it's 2D, then you can just do 2D, and the angular acceleration vector. Now, you might be thinking, well, isn't the chain, when it's swinging, the chain is changing configuration? You could think about that the way we talked about. So you could have a dynamic case here, right? This plate can pivot, so it has a range of motion. That's what the chain is like. It has a range of motion, but it's rigid along the direction that it's working. I know it's confusing because still technically the geometry seems to be changing, but that's how you have to think about it. So the geometry of this is changing too when this moves, but at least along the directions where this is considered rigid, this component, the geometry doesn't change. It's rigid. It's rigid. Along the axis of the chain, it's rigid. If this was a rubber chain trying to pull up an engine, then along where the chain is supposed to be rigid, it wouldn't be. It would deform. Okay, now this is confusing. We've got springs here attached to the rope. Well, in this case, it's not a rigid body. This is a degree of freedom. Degree of freedom in the sense that this has a degree of freedom to move, to rotate. But in this case, there's a spring attached. It would be like if there was a torsion spring in this pin. That would allow rotation, but it would have a resistance. That's the way you think about this. And and for this problem, all they're doing is you're imagining that they give you this snapshot. So this starts off, there's no tension in the springs when this is horizontal, and they're saying, what's the angle theta when we know that the springs are stretched a certain amount? Well, if the springs are stretched a certain amount, we know the force in the springs. Because of that, we can get the tension in the rope, and then we could do a free body diagram on this ring to solve for the force and the angle. But again, this is not a rigid body. It's a degree of freedom. It's allowed to move. It's not constrained to move in this direction. But you can still take a snapshot, specify, is it accelerating? So they're saying it's not accelerating. The problem is saying we pull it to this point and it stops right there. So it's not accelerating. It's still at that position. And so this still might be confusing to you. And to help with this confusion, I want to point out something. In statics and dynamics and rigid body mechanics, we use the rigid body idealization. And what we do is we apply the static analysis, the dynamic analysis, which is Newton's second law, to rigid bodies. However, we never say in this course or in dynamics, we never say that the only way we can apply the analysis that we do, the only way we can apply Newton's second law as we do, is if it's a rigid body. That's not the case. So in other words, this component could be some, strong rubber piece. You lift up the load and it starts off looking like this, and then all of a sudden it twists a bit. It doesn't break, but this beam twists here and this kind of caves in. In that deformed position, let's say it's not moving, in that deformed position, we could take a snapshot. We could take a picture of that and bring that deformed shape into empty space and do all the same analysis we do in statics or dynamics if it was accelerating. So what would happen is it would be like twisted. So you'd have it would be twisted in. So you'd have still have the pin force here. Maybe you do the same thing, but like these pin forces would all of a sudden, they wouldn't be at the same spot they're shown here. They would be like over here because it would be twisted in, right? This would be caved in. So instead of being straight up and down, you'd have a pin force kind of pointing out of the page and down, and another pin force pointing kind of, I guess, into the page and to the right. You have to specify all those directions. And then maybe like some of the weight of this beam would be like on top of the rubber piece, and it would be, pulling down on it. So you'd have like a surface force on top of this with some portion of the weight of this beam pushing on it. It would be complicated, right? It would be the shape would be weird. It would be some twisted 3D shape. But you could do that and you could solve for the forces. But the point of the rigid body assumption is that, so if statics and dynamics were going to be created without the rigid body assumption, it would be immensely more complicated. You would have to say, okay, we've got the undeformed shape, we apply the load, then we've got the deformed shape. How does the load we applied or how does the deformed shape depend on the load that's applied? Well, that would depend on the material, right? On the if it was rubber or what, it would depend on the material, on how it deformed. Well, so you have to mix in like deformable body mechanics it would be crazy. If you use the rigid body assumption, it greatly simplifies the analysis we have to do. And so this, just again, we can still apply Newton's laws. Here it was a particle equilibrium case. We applied Newton's second law it was the particle equilibrium of this ring. All of the lines of action of all the forces meet at a point. We can still apply Newton's second law, even if the body is not rigid. I mean, here, well, I guess in this problem, all we're doing is a free body diagram on the ring. So, and the ring is a rigid body. Well, technically, no. The ring with the forces on it is not a rigid body. If you think about the ring free body diagram here. Okay, let's draw it. So yes, the ring itself is a rigid body, but when you have these forces applied, the idea of a rigid body is if you, not just when you go from zero load to applied load, but when you go from zero load to any load that's within the working range of the system. Yeah, you could apply a huge load to steel and it'll twist, but like that's within the what the system is doing. But here, if we released the load, the forces would go. The ring would come up here. The forces from the string would be here. If you applied a little bit more load, then the forces would come to like here. And right, the idea of a rigid body is that the lines of action of the applied forces don't change once you apply them. So the ring is a rigid body, but this system and this free body diagram, that's not a rigid body. But again, you can still take a snapshot even in a non-rigid system and do a free body diagram. You just specify, are you holding this ring still when you took the picture, or is it accelerating? You have to specify. All right, let's take a look at another member that has some rope and a chain. So again, to reiterate, don't confuse a degree of freedom of a system, so where it's allowed to move, like this is allowed to pivot here, with the body not being rigid. And same idea when it comes to a rope or a chain or a flexible element. Don't confuse the fact that it can move. This can wobble here or whatever. This can move here. Don't confuse that with not being rigid. You think of the fact that this rope could swing, that this could swing here. This could swing back and forth. You think of that like it's a degree of freedom of the rope, just like this is a degree of freedom here. It's only non-rigid if you put like a spring here. So if this could deform, or if you put a spring here. So with that in mind, what you do is you can take a snapshot of the system at any moment in time. If it's still, then you know it's still. You just have to when you take the snapshot, you just have to specify what the acceleration is of the system. Now this would be more involved. You'd have to specify a lot of different accelerations, but if you were doing a free body diagram of this entire system, this is accelerating down maybe, and this has an angular acceleration. You'd have a bunch of different accelerations, but you get the idea. This here, they made a cut through the chain, an imaginary cut, but they don't have to put, force here and a moment here. Because right when you cut through a material, cut through a piece of metal, it can support forces in all directions. But because it's on a chain, we know that the chain itself as a unit can only support loads along its axis. It's not designed to support loads in any other direction. Loads in any other direction are going to be negligible compared to the main load. But you could take a snapshot and make a cut here, bring all this into empty space. You could just, or make a cut here and bring all of this into empty space, depin it here. Or make a cut here and bring just this gear here into empty space, unpin it here, undo this pin. But if you undid this pin, you would know that you would already know the force in this pin is going to be in this direction. You wouldn't put, if you unpin this, you wouldn't put this because you know the direction of the force. It has to be along the line of action of the rope. Okay, now Pulleys can be confusing. When I was starting out in mechanics, every time I would see a free body diagram of a pulley, it would really mess me up. So let me clear up some points of confusion that you might have with pulley free body diagrams. So you might see, for example, they'll make a cut, a free body diagram where there's a cut across here, and you've got and then they put, and then I guess the weight of the pulleys would go here. Something like that. And it just seems like, well, man, that's not rigid. How is the connection between the rope and the pulley rigid? This is how you have to think about it. So first of all, you're going to hear the term frictionless pulley. What does that mean, a frictionless pulley? What they're talking about, they're not talking about the friction between the rope and the pulley. They're talking about the friction in the bearing here. They're saying that, like, so if you had a pulley that was really rusted and it's trying to roll, well, there's a couple moment then that's resisting the rolling. Or if that pulley was holding up a load, well, there's a couple moment that's helping to hold up the load because it's preventing the roller from rolling, right? A frictionless pulley is saying that this is perfectly smooth. There's no couple moment in the roller, okay? It doesn't have anything to do, that term frictionless pulley doesn't have anything to do with saying that the friction between the rope and the pulley surface is frictionless. In fact, the way you think about it for an ideal pulley, it's the exact opposite. It's actually it's like perfect friction. In other words, if we come here, in this scenario, right? This isn't a pulley, it's a gear, but it's kind of like perfect, like quote unquote perfect friction because the gears are meshed. There's no slipping here, right? This can't slip. I mean, if it slips, then one of the gear teeth have broken, right? For every degree that this spins, the gear spins, the chain is moving that corresponding amount. There's no sliding whatsoever. Well, in reality, there could be sliding here, right? If it's not a gear, just a rope, just a friction between the rope and the pulley surface, there could potentially be sliding to some degree. Well, in an ideal pulley, there's no sliding. Now, it's still not rigid in the sense that the pulley, the rope can move, but that's a degree of freedom. That's rigid body motion. Okay, so in that case, you can take a snapshot at any point in time of the pulley rope system, pulley wire system, and do a free body diagram, right? Because you can think about the rope and the pulley together as rigid. You could do whatever you want. You could make just a cut here, a cut both places, and take all of this out into empty space. Take all of this out. Maybe you could make a cut here and take all of this, unpin it here and take all of that. Make a cut here and unpin the roller here and take all that out. Do the pin here and take all this out, however you want to do it. Okay, now, we haven't looked at many examples of free body diagrams in 3D. However, what I found is that even when I was confident with free body diagrams in 2D, when I went to 3D, it was still hard and intimidating. But the reason why it's hard, you might find the free body diagrams in 3D harder, is not because the concepts of a free body diagram in 3D are harder. What happens is when you're so used to working in 2D, you really don't have to work much with vectors. So yeah, you have force vectors in 2D, but it's different. You're not really working with, that whole vectors in space video where we go through the coordinate direction angles, the alpha, beta, gamma, really having to use the dot product to project vectors and create vectors in 3D and understand them and understand how vectors work. You don't really have to do that in 2D. And even more so, you moments as vectors. You totally forget about when all you're doing is working in 2D. Because in 2D, the moment vector is into or out of the page, so it's just a positive or negative moment. So you just forget about the moment as a vector, and because of that, you forget about what the definition of a moment is. The cross product for a moment, R cross F. And that's the reason why it's so hard to all of a sudden do a free body diagram in 3D, or work a statics problem or dynamics problem in 3D. It has nothing to do with the principles of free body diagrams, the concepts. It's not being comfortable with vectors, vector operations, moments, moment operations, projecting vectors, all that kind of stuff. And so it's really important to go through chapter 2, which is on force vectors and vector operations. So go through the videos on chapter 2, watch there's that hour and a half long video just on vector operations. Go through the moments chapter, understand moments as fixed vectors, moments about a point, moments as sliding vectors, moments about an axis, moments as free vectors, all of that. Simplifying force couple systems, and you can think about it in 3D. If you're really comfortable with those concepts, then coming to a free body diagram in 3D is not a problem at all. Why? Because, okay, you do the same process. You bring a component or a system of connected components into empty space. Typically, you're just dealing with the body forces. Typically, you're just dealing with gravity. Get the center of mass in 3D. Finding the center of mass in 2D or 3D is the same thing. The process is the same. There's just an extra dimension. Put the weight acting at the center of mass down or toward the center of the earth. It depends on how your coordinate system is oriented. Now, surface forces, if you have like a wind load or whatever, if it's in 3D, it's in 3D. It's a vector that's in 3D, or a distributed load in 3D. Now, for like support forces, if you remove like a bolted connection or any kind of support, it's the exact same idea as we did in 2D. You're just saying, what is this support? What kind of motion is it resisting? Okay, so if we brought this entire component into empty space and we made like a cut here on the rope or the string, whatever that is. So we don't bring this rod, we don't bring these connection points here, we don't bring all of this. Okay, well, what motion is this resisting? Okay, well, this connection point here, what motion is this connection preventing this from doing? Is preventing it from moving in the X or the Y, not the Z. So there's going to be, this wouldn't be here, the rod wouldn't be here, but we'd put, let's say these are unknown forces, we would put just any direction there, but there's no force being resisted in the Z, or at least it's negligible. Or if it's negligible, if this is like a smooth, assuming the friction is negligible. Okay, what else? It's not preventing rotation about the Z. It's preventing rotation about the X. So we'll put this in the positive direction. And it's preventing rotation about the Y. So we'll put that in the positive direction. Okay, here, this is just preventing translation up in the Z direction. So we'll put it up. It'll be up. Here, this is just preventing translation in the X direction. We'll leave this force is like an external force. We'll just leave that. We'll just put it as it is. And then here we would have a cut here, but we know the direction of this force. It's along the line of action of the rope, so we know its direction. And then I guess we'd neglect the weight here. But we could put the weight. I guess the center of mass would be maybe here, going down toward the center of the earth, or wherever the center of the earth is. You don't have to. The center of the earth doesn't have to be down, but typically it is. Right, so what's the challenge? It's the 3D vectors, the moment vectors in 3D. So going from a 2D free body diagram to a 3D free body diagram, as far as the concepts of a free body diagram go, just the concepts of the free body diagram, it's simple. If you find concepts that are associated with the free body diagram confusing in 3D, then I would bet that you also find those same concepts confusing in 2D. Okay, now I mentioned this before, and I want to go over it again here, but a general free body diagram. Here's a completely general free body diagram. Some random shape material that's not symmetric in 3D, right? You've got force vectors applied that in 3D, and you also have couple moments applied in 3D. That is the general free body diagram. Okay, now notice these are couple moments. And there's no moments. Like we talk about moments about a point, those are fixed vectors, or moments about an axis. Those don't exist on a free body diagram. At least the initial raw free body diagram. You can add them later for analysis, but the initial raw free body diagram, there are no moments about a point or moments about an axis. It's just couple moments and forces. And so why is that? Now you might be saying, well, okay, we've been doing all these free body diagram examples, We had the skyscraper. We put moments here, right? This was the forces, but we also did the other example where there were, you had, and then, right? We put moments at each of the connections. We just put moments here. Those aren't moments about points like that. These are moments about E, right? No, those are couple moments. So the moments that at supports that you put, technically those are free vectors. You could put them wherever you want, but we put them at the support just because that's the most clear of where the moment's coming from. But those are free vectors. These are free vectors. You could put them anywhere. Okay, so but why can't we have moments about points? All right, well, the reason is because moments are something that humans have made up to describe a nature of a force, right? When you think about a free body diagram, just like if in the caveman times, right? I mean, if there's just a general free body diagram, as far as a caveman is concerned, the only thing there are forces. That's it. You have a body with forces on it. That is it. There's no such thing as like something in physical reality that's a moment. That's something we've made up, right? So going to the caveman times, if you have a free body diagram with just forces, well, you could observe and say, I noticed there are some forces that I can find pairs of forces that are the same magnitude, opposite direction, and separated by distance. And so you could turn that into a couple. And that's what we do here. We just say, okay, we'll go ahead for the general free body diagram. If there are forces that we can make as couple moments, we'll put them that way. We'll remove those two forces. We'll remove the, this pair of forces here, equal and opposite and separated by distance, and just put the couple moment. Or you can think about it like, so when we went through chapter 4 and we talked about simplifying force systems down to a resultant force and couple moment, or like a wrench, the idea was we start with a general force system, actually force and couple system like this. So just a general force, and the couple moments come from a couple moment like that you turned into these two forces that you turned into a couple moment. From there, you can reduce these forces down to different forces, move the forces around. But the only thing you create are other resultant forces and couple moments. There was no situation where we reduced a force down to a moment about a point, right? You couldn't do that. You couldn't say, I'm going to reduce this force down to a moment about this point, just like a moment about a point, a fixed moment. Moments about points are just something we use for analysis purposes. We use moments about points with Newton's second law of rotation, where the moments about a point, the sum of the moments about a point are proportional to the angular acceleration about that point. But that's not part of the free body diagram. We don't, like, you might have like if you're designing an engine that has a rotational shaft output, or a wrench, some sort of wrench thing that's rotating a bolt. Well, part of that design, you might say, okay, I've got my free body diagram, and as I work with the free body diagram, I want to calculate what the moment about that point, that bolt axis is. And so as you work with the free body diagram, or change the design, you're always monitoring what the net moment about that point is, or about that axis is, that bolt axis is. And your whole design is dependent on, you want to get the right moment about a point. Sure. But that's not part of the free body diagram. You don't represent on a free body diagram a moment about a point, like as an inherent force on the system, like you do a couple moment. You see? Okay, now last thing to talk about is on a free body diagram, on the free body diagrams we've done so far, there's two types of forces. There were the forces that came from, they're called external forces. They came from the environment. And then there were forces that came from a connection. The forces at connections are called reaction forces. Those are called reaction forces. The forces coming like from the environment are called external forces. So the force from the wind on the skyscraper, that's an external force. That's not coming, you didn't have to remove a connection. When you brought the free body diagram of the skyscraper structure into space, you didn't have to remove a connection. And the wind force was associated with that removed connection. The car, so the force on the tires. You didn't unbolt something or remove material, or make a slice through a connection through the body. That's an external force. A person standing here, that's an external force. Gravity, that's an external force. If you meet a slice in the rope here or a slice in the chain, these are reactions. Those are like connections, right? They're connections where you have a degree of freedom to swing the ball, but the force in line with the rope it's like a connection. You're removing a connection. You're removing a connection here. Those are reaction forces. The load on the shaft of an engine. That's not a connection. That's an external force. And so we talked about how to analyze what forces to put whenever we remove a connection and we have to add forces corresponding to that connection. We talked about how to rationalize this. You think about what motion is this connection preventing the body from doing. And then if it was preventing motion, then you put a reaction force in that direction. If it wasn't preventing motion, you don't. And typically reaction forces are unknowns, but they don't have to be. Maybe you know, I know that the force in this pin is going to be, I want it to be this force. So what is the external force going to be to correspond to that? You could look at it that way. And so in the statics book, they go through all kinds of different connections. And we're not going to go through all of these. You could Google this, take a look at it yourself. But if you go through each one of these, it's a simple analysis just like we did. Like this roller here. Where is this roller preventing motion? If we took this whole body, the body here into empty space, what is this roller preventing? What motion is it preventing? Motion in this direction. It's not preventing motion in this direction. It's not preventing any rotation. Now, as far as motion into or out of the page, that's not a part of the problem. So motion into or out of the page or bending into or out of the page should be negligible, or else you need a roller in 3D. But you can extend this to 3D. You can extend all of these to 3D with no problem, right? So a rocker is different from a roller. With a roller, the force line of action is fixed. With a rocker, it depends on the snapshot in time you take, right? The theta depends on the snapshot. Okay, and remember, for a reaction force, like here we go, this is preventing motion in this direction, and it's also preventing rotation. This is a couple moment, right? The reactions are the couple moment and the force, which acts perpendicular to the rod. These are couple moments. Even if you have an external force for a free body diagram, that external force is going to be represented as a couple moment. If it's a moment, it's going to be a couple moment. In nature, forces and couple moments are applied to bodies. Moments about points are just an analysis technique to understand if the body is functioning the way you want it to function, right? Fixed supports resist translation in all directions and rotation in all directions. And remember, you can extend this to 3D easily. You just put an extra force in the X and the extra 2 moments. And around town, wherever you go, you'll notice all these different types of connections. Welded connections, those are fixed supports, right? Here's a rocker. Here's a pinned connection. Here's another pinned connection. All right, so that's free body diagrams. I know this is a long video, but this is such an important topic. I wanted to make sure I went through it slowly and carefully.